words, encouraging people to start and work on dye-sensitized solar cells. But later, when things I will use the word grew up, then I thought that I should add up something, some basics, initial things which are required for starting research in polymer electrolytes. And therefore, I added the word, the polymer electrolytes and overview. So generally, it is a review on whatever has been done so far. But my attempts, my efforts shall be towards the information, so that anyone who wants to start research in polymer electrolytes can do something, so that simply adding polymer and then saying polymer electrolytes, that may not help that much. Let me try to share my slides if I can. I hope the full screen slide is visible now.
Yes, it's visible.
Okay, thank you. So the first part of the talk today, that will be on polymer electrolytes. I believe that you people must have enjoyed the talk of Professor Arof, one of the senior workers and a good friend of us. He elaborated more towards the impedance spectroscopy and how one can analyze the impedance spectroscopic data. So I will try to skip those analysis part, but definitely we'll touch upon that what information we gather from all these things. So the flow will be starting with polymers. What is a polymer? Chemists who are linked with this, they know it very well, that when we repeat small unit monomer multiple times, then polymer can be formed. The process called polymerization, and it may be a naturally repeating process where we call that the polymers are natural, or one can synthesize, do some chemistry, polymerization, controlled polymerization, and have long chain. We all sitting across the web, we are also made up of polymers. Those are based on carbon. But at the same time, one may have polymers which are non-carbonous. Silicon is one of the common example, which has very similar properties like carbon. And the silicon-based polymers are very well used for their different properties, most commonly for their biocompatible properties. Depending upon the structure of the chain, they can also be classified as linear, branched, cross-linked, and other varieties. But anyway, lies towards polymer electrolytes. So therefore, let us go towards the polymer electrolytes. The first line is very important, and I read it, that polymers made to conduct via ions. Polymers in general, they do not conduct. The conjugate polymers that are available and which conduct, they are generally not electrolytes. They conduct via electrons or holes. In general, they are semiconducting polymers. Whereas if we can make the polymers conduct via ions, they work as electrolytes. So different polymers can be made work as nature of the, depending upon our purpose, we can modify them. The interesting property of the polymers, especially their flexibility, the free-standing formation capability, the easy processing, and at the same time the lightweight, that makes the polymer electrolytes very interesting and very important material for the use in the electrochemical devices. To mention here, the batteries commonly used in our laptops, in mobiles, lithium-based batteries, they generally contain lithium polymer electrolyte. Most of the batteries, it is now printed on that lithium polymer battery. And unfortunately, we lost one of the Nobel laureates a couple of days ago, John Goodenough, who is one of the discoverers of lithium composite, the lithium polymer battery. So, polymer electrolyte, and accordingly polymers are classified. Electrolytes are also classified. So if the circle at the center, it is a polymer electrolyte, and one may have one plasticized polymer electrolytes where the polymers are plasticized using some molecular or like, and when they work as polymer. Second category as gel, but they were close to the first one. But the difference is that the gel polymer electrolytes, liquid is trapped in the rigid network of the otherwise polymer. For example, a rigid network of polymer like polyethylene, which has a high glass transition temperature, and in that we or any similar product, and it can remain inside. Then forms gel polymer electrolyte show pretty nice properties. Here we use classify.
I think Bhattacharya sir has a meeting. Yes, sir. Connections unstable. सर आपकी आवाज नहीं आ रही थी, अनम्यूट कर लीजिए.
तो डिस्कनेक्ट हुआ तो मेरे ख्याल से सब कुछ
वो डेफिनेटली क्यों ऐसे हो.
ओके, तो सेम स्लाइड पे आ गया ना वापस.
हाँ सर, वापस आ गया.
So the solvent category now generally we don't name it like that. Earlier we used to call them as solvent polymer electrolytes, and the most common member there was PVA, polyvinyl alcohol. And this is a very common type of polymer we often use in paints and adhesives, where we know that incorporation of water molecule inside the polymer network, it swells up, and then the ions, most commonly the H plus and OH minus ions, they use to move like anything very fast. But the stability of these polymers, they are quite doubtful, because if it is water incorporated, then it will be strongly humidity dependent. And therefore, for the real application purpose, this type of solvent category that is not that much used in the electrochemical devices. The next composite polymer electrolytes. Composite, and for last almost 50 years, people are using composite electrolytes, starting from Liang, if I am correct, then 1973 and onwards, where he started mixing two solid materials, and the two solid materials, they remained in their own phases. So composites, they are defined by that only, that if two or more compounds are mixed together, physically mixing only, no chemical bonding, they remain in their own distinct phases. But due to the surface properties of the compounds, surface charge, the variety of other concepts, they also come in. The conductivity can shoot like anything, multiple orders. So similar activity, similar property can be achieved when a solid, maybe very inert, most commonly the oxides, the inert oxides like Al2O3, SRO2, and silica also, these things are mixed with polymer, then the conductivity can be modified. The interesting part in this is, which stands quite tall, that when we add fillers, which are tough materials, which are inert oxides, they give good mechanical strength to the polymer film. And therefore, this category is pretty used and liked by the people. The next category that stands is polymer salt complex. Sometimes we add a word solvent-free polymer salt complex, or call them as dry-solid polymer electrolytes. This is something where we generally work in, because we believe that it becomes very easy to prepare and get rid of all the trouble, plasticization and gel incorporation, making composite. All these troubles we can get rid of and prepare a polymer salt complex. Now, quite recently, not very, but still quite recently, people have started making it in two other ways. One, we add some salt in a polymer, go on adding the salt, and up to certain limit we add the salt and see how the conductivity is changing or how the properties can be modulated. The other part is we take a salt and add polymer into that. So it is either polymer in salt or salt in polymer. Both the categories, they can be explored and studied. So when we talk about the polymer salt complex, the most common example that comes in our mind is polyethylene oxide, where we have we chain something like this, CH2, CH2O, and there is this ether group which is available. This ether group allows the cation, the salt that we add into that, cation of the salt to attach, and that salt, I hope, yes, I will use this slide and then again go back. So if there is a chain, long chain of the polymer, then with the ether oxygen, these gray balls, they are ether oxygen in this figure, they can allow hydrogen bonding of the cation like this. So if, say, for example, if we add lithium iodide in the polyethylene oxide, then this is the lithium ion that gets attached with, where is my cursor? Yeah, this is the lithium ion that gets attached with the oxygen ion, and it starts hanging outside the chain. The anion, the poor fellow, it moves around, though it remains closer to maintain the charge neutrality, but it moves around in the electrolyte. Now this cation, this can be made to jump from one ether site to the other ether site and the third one, and so on. That makes this system conductive. Now, how that can be done? Let us look back. So there are a variety of possibilities how we can make these ions move from one point to the other point. The focus shall be towards the enhancement in the conductivity, because ultimately, when we are talking about the use of a polymer electrolyte in any of the electrolytes, the battery or latter applications, the conductivity is a very important factor, because if the conductivity is not high, the internal resistance of the system, of the device, that will become high, and that may hinder the process, whatever we are expecting, the charge migration at least. At the same time, offering high resistance means I square into R, heat will be generated. That may hamper the activity of the device. We often notice that in, I will name the company of mobile companies, the battery gets very easily heated. Well, when we use for continuously for some duration, the battery gets heated up. That is not desirable. So the methods of increasing the conductivity, enhancing the conductivity are, again, copolymerization, adding fillers, plasticization, and maybe for last 10 years, people are adding low viscosity ionic liquid into the polymer electrolyte. So how they do move? How they do move in the polymer system? If this is the configuration, it is a simple cartoon drawing. This is the configuration of a polymer electrolyte film. The lines which are very periodically drawn, they indicate the crystalline region of the polymer film. Crystalline region, I mean that the polymer coil is very regularly, rather, I correct my sentence, polymer chain is coiled in certain regions, and the irregular part indicates that the polymer region is uncoiled, open. Now, if we take the polymer above its glass transition temperature, then it starts breathing and unbreathing. So the chain becomes flexible and it starts moving. When it starts moving, then, for example, if we look at this diagram, then if earlier it was connected to this ether oxygen, maybe this part, while moving, it may come closer and feel that this is the same energy point, and it can hop from this part to that part. Now, once it is connected to this ether oxygen, and if it goes again, flips on the other side, effectively the ion which was attached here, now that has gone there. And by this chain flexibility mechanism, the ions pass through from one end to the other end, or we say that they are conductive. Now, the parameters here will remain the two, because conductivity, we know that is a product of the number of charge carriers, the charge being carried by them, and their mobility. The charge being carried by them will remain fixed. Either it is a monovalent cation or a divalent cation. So it is 1 or 2 at most. The other two parameters, the variables, will be N, the number of charge carriers, and their mobility. So the target should be that how we can increase these two in N and mu. And at the same time, while we are talking only about increasing, unless we measure them, unless we calculate the value of N or mu, we cannot think of how we can increase them. So we need to think of how we can measure or how we can calculate the value of N and mu. Please. Yeah. So the preparation is pretty easy. Unlike the semiconductor processing, the processing of polymer electrolytes, synthesis of their film is pretty easy. My focus will be towards these polymer salt complexes, and there what we do, that we take the polymer in any of the solvents. For example, if we are concentrated towards polyethylene oxide, one can choose methanol, one can choose acetonitrile or similar solvent, and then add the salt in desired quantity into that. The story started with monovalent cation also. Now it is, there is a broad classification, and we know that which type of cation can be attached and move in that. Maybe in one of the slides later, I will show that there is some slight selection rule that what type of salt you should choose, what you should not. Anyway, you mix them well so that both the polymer and the salt, they get mixed. It is only not mixing as a solution, but their complexation is required, and therefore this stirring needs to be continued for quite long time. Generally, we talk about 6 to 8 hours, not less than that. And once it is mixed, then it is poured into the Petri plates, maybe glass, maybe polypropylene. Those who want to start with this, they should take care that the plate surface, the bottom surface of the Petri plate should remain flat. If it is not, which is quite often possible because the central part of the Petri plates are generally slightly elevated. So the thickness of the film will differ and the uniformity will be a challenge. So anyway, once they are poured into Petri plate, they are left for drying. The words are very interestingly written here, to dryness, I don't know. But anyway, they are left for drying in the room ambient. And then for ensuring that the solvent that has gone off, these films, they are placed in vacuum so that whatever solvent we had used initially for dissolving them, that can be taken off. Ultimately, we are left with a polymer film that contains salt. Better to say that salt dissolved in polymer, which is self-standing, something like a paper. Once you have something like this, then the business of characterization that starts. One can go for the structural characterization. I have intentionally removed X-ray diffraction. If it is crystalline, then only something can be obtained out of that. If it is purely amorphous, then only the amorphous. The classification and identification of very complex. That's why intentionally not included that. Then one should go for the thermal characterization also, because ultimately we want to use our device, we want to use our polyelectrolyte in some device, and that device may undergo thermal fluctuations in any country. In our country, last fortnight the temperature was around 44 degrees, and in winter it will go definitely less than 4 degrees. So can our polymer withstand all these fluctuations, or the property will change like anything? So therefore, thermal studies are very much essential. Generally, we go for DSC or DTA. TG is not that much required, because once you choose a polymer, you know what is the thermal stability range. You know how the weight can change and it can decompose. But the melting and glass transition, these are very two important parameters. Therefore, one should study. And finally, it is the electrical characterization. Since it is an electrolyte, ion conductor, and therefore impedance spectroscopy is one set of results, so that you can understand that what we expect of it. So how a film looks like when you pour the mix in a Petri plate, it appears something like this, and then you can take that transparent, hopefully transparent, depending upon the self-standing polymer electrolyte film. And under the POM, the polarized optical microscope, if it is polyethylene oxide, it looks something like this. Now, these interesting flower-shaped region, we call them as spherulites. They are the crystalline pockets. What I mean by crystalline pockets is, again, these ordered region, where the chain coiling is pretty ordered. They are these spherulites. These spherulites may be big, may be small, depending upon many things. And the most common thing is the concentration of the salt. Depending upon the salt concentration, depending upon the nature of the salt also, the size of these spherulites may vary. Earlier, we used to say that it is only the amorphous region where the ions can migrate. But now that has been corrected, and we say that ions can migrate through the amorphous region predominantly. They do migrate through the crystalline region, but the conductivity is poor, and therefore one should try to focus that how we can increase the amorphicity of the polymer matrix, can reduce the size of these spherulites, and even the number of these spherulites. Though number is not in our control, but the size of these spherulites is pretty much in our control, and we should try to reduce them. Here in this slide, you can see that how the size of these spherulites, they vary based upon the nature of the salt. All these were the iodide salts, starting from lithium iodide, where the spherulite size is cursor. Anyway, it is written here. I'm not getting my cursor. Yeah, now I've got it. So this is lithium iodide with pretty large size of spherulites. Sodium iodide even much larger than that. Potassium iodide smaller, and this is the reason why we people, especially the solar cell people, we like potassium iodide as the salt in the electrolyte. Going back to ammonium iodide, again the size is similar to lithium iodide. Interestingly, it was believed that ammonium iodide, it should give a proton, the conducting species, which is the smallest possible. So the proton is supposed to be the smallest one, but somehow that doesn't match with their behavior, and it appears that it is the entire NH4 plus ion that contributes to the conductivity. And when we go to the ionic liquids, which are very big cation, the imidazolium type of ionic liquid, then depending on the size of those cations increases. So this can, be used as a guideline that while choosing the nature of the salt, while choosing the cation of the salt, you can decide that how amorphous your film will become. More amorphous the system, probably the conductivity will be more. I am using the word probably because this is not the sole factor to decide. There are other factors also, but this is one of the patterns that one can choose it. Coming to the next characterization technique, that is the thermal characterization, differential scanning calorimetry. So if there is a slope change that indicates the glass transition temperature, the crystallization is generally not observed in this type of system. The melting is pretty much observed where it melts. Since it is a mixed system, not a perfect crystalline, partially amorphous, therefore the peak is generally broad, not a single sharp peak. The bottom, this diagram is one of the examples with PEO type of polyethylene oxide system. One can see that how broad the melting can be seen. The polyethylene oxide has a glass transition temperature around minus 60 degrees centigrades, well below the room temperature, therefore can nicely be used below any temperature than its melting. Starts melting somewhere closer to 60 degree, varies depending upon different parameters, 60 to 68 degree, sometimes even beyond. Anyway, minus 60 to plus 60, which is a sufficient wider range of temperature where it can be used. Now here comes the ionic business. When we talk about electrolyte, it should be perfectly ionic conductor. And though we write that the total conductivity should be sigma ion plus sigma E, but we don't expect anything sigma E. So the simplest way of measurement is the polarization technique. What we do that we take the electrolyte. This is common for any type of solid electrolytes, be it crystalline, be it polycrystalline, or even polymers, and we sandwich them between two electrodes. The theory of Joe Wagner says that one of the electrodes should be non-blocking and the other one should be blocking for the ions moving into that. Often it is not possible for us to do like that. Often it is not possible. And therefore, what we do, that we use two blocking electrodes, simply two blocking electrodes. So instead of getting a varying slope, we get immediate sharp polarization, and then it saturates. So one should monitor this current for quite some time, ensure that there is no further drop in current, and using the value of initial and final current, we calculate the contribution in conductivity by the ions. Ideally, we expect this to be 1, but we generally don't get it to be 1 because the charge cloud formation is so fast and so quick that the measurement of initial current that becomes erroneous. You do anything, you do whatever machine you want to use, this will not give you the exact value. This may give you closer, but not exact. And therefore, this gives a lower estimate of the value. If you are getting, say, 0.96, don't get demoralized that I am getting 4% of electronic conduction. It is giving you 100%. That 4% is only measurement error of your machine, not yours, of your machine. Now, this also gives some hint about the conductivity of the material, because this drop, say, for example, if I look at this P curve or the right bottom, I can simply say that the conductivity of this one is poor than this one, because the charge cloud formation, this is much faster in the lower one than the upper one. But this is only a quantitative thing, qualitative thing, not quantitative. Make it quantitative, one should go for the impedance measurement, and these are some of the Nyquist plots. You can estimate the bulk impedance from the first intercept of the curve. This one, the first intercept will give you the bulk impedance, and then using the relation that 1 upon RB into T by A, L by A, you can calculate the conductivity. Now, this is a typical curve. I should confess here that most of the results that, or even the slides that I am using, they contain the results of Dr. Sandhya, one of our colleagues, and Dr. Anubhavi, they worked on the polymer electrolytes. So I quickly, captured the diagrams from their thesis. Happens that when you add even 5% of a salt into the polymer, which is otherwise insulating, the conductivity of otherwise, when the salt is not added, the conductivity is generally of the order of 10 power minus 10 or 11. So when even a 5% of the salt is added, the conductivity shoots up. This jumping up of the conductivity is due to the release of ions. When the salt is dissociated, immediately some ions are released, and therefore the conductivity shoots up. I'm sorry. Then further, it increases with increase in the amount of salt. Now, how much salt? That depends upon many things. But anyway, this is the general trend. So the conductivity will increase. This increase will mean that I am adding more and more ions into the electrolyte. But after that, it drops down. This dropping down is generally due to the formation of higher charge multiplates. Now, this is something which is very uncommon from the liquid electrolytes. In liquid, since everything is mobile, is a fluid which is moving here and there. So therefore, though it may form higher multiplates, but we don't bother about that. But in polymer, once a charge cloud is formed, it will have its own solvation cloud, and therefore it will become very difficult for that entire bigger cloud to move through. And that makes the conductivity drop down. So the conductivity drops down. One may continue with low conductivity or get a slight increase in the conductivity. That is due to the either redissociation of those clouds or the movement of those clouds throughout due to the increase in mobility. The amorphosity increases and the mobility therefore increases due to that. So that depends upon what type of salt, what is the nature of the matrix, but broadly this is the common feature. This diagram is again, it indicates some interchain and intrachain hopping that I already talked about. These are some routine type of measurements to the dielectric constant, how the dielectric constant varies with composition, because the dielectric constant is a direct measure of the charge collected inside. And then one must know how the dielectric constant is varying. Now, earlier we used to calculate the dissociation factor. What do we mean by this is that when we add salt into polymer, then we expect that all the salt, all the molecules, they must get dissociated. But whether they have got dissociated or not, that is an important factor. And therefore, to understand that whether all the salts that we have added, they are getting dissociated or there is something wrong with that, one should calculate the dissociation factor. So it is a ratio of n by 0. And based upon the dissociation energy, the electric constant of the material and the temperature where we are talking about, one may get different types of pattern and then choose that where should I work? What should be my limit of salt that we are adding? The number of charge carriers. Earlier in one of the slides, I said that it is the mobility, it is the number of charge carrier. These two are the important parameters. And therefore, one must try to calculate N and mu. Unfortunate thing is there is no direct measurement of N or mu in the electrolyte system. And therefore, there are a variety of other formula and indirect techniques, I would say, for calculating the mobility and number of charge carriers. One of the theory given by, difficult to pronounce, Schatten-Gerdes, that is given here. There are other formula also. Maybe in next slide, I will show the Trukhan's model also. They are based upon different considerations. This theory talks about the purely glassy matrix, assuming that the entire matrix has become glassy, amorphous. The value of mobility and number of charge carriers can be calculated. Dr. Amit and one of my students, they are coming up with some guideline on these also, that what type of theory you should apply for calculating N and mu, which theory on which type of system. Maybe it is Schatten-Gerdes, maybe it is Rice-and-Roth, maybe it is Trukhan's model. How to decide what is the deciding factor? Maybe very soon they will come up with those those data as a paper. When we look at the Tukhan's model, this is based on the space charge type of consideration. The diffusion of the ions throughout the matrix, that becomes important here, and therefore one need to calculate the tan delta and use that tan delta, the loss factor, for calculating the ion diffusion coefficient. Use that D in the Nernst equation and get the value of N. The broad difference between the Tukhan's model and the Schutt and Gardez model is that in one case, the number of charge carriers that may go beyond the Avogadro's number. This is something which is physically not acceptable, because if the number N is going the Avogadro's number, it means effectively it means that the charges are even outside the matrix, which is not feasible. In many of the papers, you will find that the temperature dependent behavior is discussed. Now, what do we mean by temperature dependent behavior? Number one, polymer will melt at certain temperature. Number two, the activation energy of the ions that is required for hopping from one point to the other, that is given externally to the ion, and therefore the conductivity should increase. So both the things that can be observed, that if we are working at a temperature which is below the melting point, we can have something like this. And in that pattern, the crystalline region, maybe the ion not that fast. But however, once these crystalline pockets, they melt, the entire matrix becomes amorphous and the conductivity shoots up. This is a very common general behavior of the polymer electrolyte. The thermal conductivity, that straight line following the Arrhenius type of law, may not be a straight line. We need to choose a pseudo temperature, a reference temperature as T0, and then talk about the VTF, Vogel-Taman-Fulcher type of behavior. But anyway, that will be too much of theory here. I skip that. These are again the routine type of observations that we need to make. We need to look at whether there is any electric polarization or not. If the polarization is too fast, if it comes down to very lower frequency, we should try to avoid that type of system. We should try to make it higher and higher so that it can go to the higher frequency values. This is the tan delta, which is used for calculating the diffusion coefficient for the Tukhan's model calculation. Similarly, the dielectric modulus, this is also one of the important parameters to understand the behavior, what exactly is happening inside. Now, why I'm showing only these things, because we physics people, we love to think about the dielectric parameters. May not be very much, interesting for the device people, but at least for understanding the physics, what is happening inside, we need to look at these. Now, when we talk about polymers, then people often comment that these are very hazardous. We often shout that polymer, no plastic, no plastic. So one can look at the biopolymers also. Biopolymers can be derived from plants, animals, microbes. Accordingly, they are named. Their nature is also different, and they can also be made to conduct via iron. See, if, for example, this is one of the biopolymer electrolyte derived from palm. We call it sago palm. So that can be dissolved in different solvents. If it is dissolved in water, if it is in DMSO or DMF, the nature of the conductivity, though the salt remains the same, the polymer remains the same, nature of the conductivity, that varies. And here the importance of the measurement of dielectric and those things, that become very important. Trying to sum up the polymer part, because I think I have consumed enough time so that I can quickly look at the solar cell part. Most commonly, the polymer electrolytes are used in fuel cells and batteries. It started rather with batteries and fuel cells only. Then last couple of decades, people started working on supercapacitors, sensors, little bit, not more than that. But solar cells, probably very rare. because people don't look at the solar cells. The polymer electrolyte people, they don't want solar cells to barge into their own regime. And therefore, this is the least approached device by the polymer electrolyte people. Coming to the polymer electrolyte based solar cells, we'll try to move faster because now it is already 12:15. So if we look at the data, then the highest efficiency is given by the crystalline part, crystalline solar cells, the silicon gallium arsenide based solar cells. They do not use polymer electrolyte or even any electrolyte for that matter. The second generation are these green lines. They are based on thin films, and these thin film based solar cells, they also do not use any electrolyte. It's only the orange lines where one can look at and find out the role of polymer electrolytes. Most commonly, it is the dye-sensitized solar cells. If we compare these solar cells, then as reported by Martin Green's lab, then you can see that the crystalline system, they give pretty high efficiency, but they are very expensive, and therefore that is the reason why the third generation solar cells, they came in, and they are based on the electrolytes. Now, we used liquid electrolytes in these devices. Setup was very simpler. In a vessel, in a beaker or something, a container, a semiconductor electrode was immersed and a counter electrode was immersed, and an electrolyte, may not be polymer, that was used. But the conventional problems of the liquid remain as such. So we started with something like this. This is a very planar structure. The base is a ITO coated glass plate. This surface, front surface, is conducting. On top of that, we spread polymer electrolyte. I used to have a spin coating system for that, so that we can achieve a thickness of the polymer electrolyte of the order of 1 micron. And on top of that, we used to place crystalline silicon, P-type, N-type, both I have tried, and then took a connection from the top of the ITO coated electrode here and the back side of the silicon. So back contact part, that remains important, and this interface, the polymer electrolyte silicon interface, this worked as very similar to that of a PN type of junction. Interestingly, it showed a junction behavior. The VOC was in hundreds of millivolts, but the conductivity, the current remained very low, and the maximum conductivity that we could achieve was 1.1 microampere per centimeter square. Now, in those days, the Skothim and Ingana's group, they reported very close to 10 milliampere per centimeter square, and finally we could find that the size of their cell, that was only 0.1 centimeter square only. So if the size is 0.1 centimeter square, to be more precise, 0.15 centimeter square, it means at one side 3 mm, the other side is 5 mm. Into that, you are measuring the solar cell. It is impractical. There is no practical meaning. Anyway, this gave some hint that yes, polymer electrolytes that can be used for the solar cell application. But unfortunately, since the current was low, so people they tried to discourage us that no, this is something which should not be explored. Skothim did that because Skothim's main focus was towards the semiconducting polypyrrole, polythiophene type of polymer. It was not an electrolyte. We continued probing it, and we entered in the third generation, the dye-sensitized type of solar cell could use, and still we are using that. Now, in a dye-sensitized solar cell, what we have is transparent conducting oxide, generally the FTO glass plate. On top of that, we arrange the nanoparticles, generally TiO2 written here, and dyes are absorbed onto the TiO2 surface. The electrolyte is poured in, and it is closed by the other electrode, which is a platinum coated, again, transparent oxide. So this is one of the old photograph showing the colorful dye-sensitized solar cells. This is something which is demonstrated by the Malaysian group, the flexible type of solar cell. Now, the important part that comes in is the electrode. What should be the nature of the electrode in terms of the use with polymer electrolytes? Now, see, if you see, you can see these right-hand side photographs. It must be porous. We name it as mesoporous. And at the same time, when you are using a polymer, then it should allow the polymer to get good contact with that. If the contact is not good, the polymer will get detached after maybe a couple of cycles, and the cell will become dead. And therefore, the roughness of the surface becomes very important. The surface must be quite rough, quite dirty, so that not dirty means dirty, but quite rough, so that the polymer can trap into it and make a good bonding with that and remain attached with it. That's why the formation of the electrode is again very important in case of polymer electrolyte based DSSC. These are some of the photographs. Then on the counter electrode, since the role of polymer at this site is not that much important, the role is here the redox activity, and therefore the choice of the counter electrode material that becomes very important. Most common is platinum, few islands of platinum, but other derivatives, say carbon, graphene, RGO, stainless steel, these can also be tried, and people do try that. I will not explore those things here. That will take another 1 hour talk on these only. Coming down to the electrolyte, this is the electrolyte which was reported by Pengwang and Brazil. This gave 13.6% efficiency, but not a polymer electrolyte. It was ionic liquid. I will skip all these. Yes. Now, if we use the polymer electrolyte, the entire fabrication business becomes very simple. Once you create a dye-soaked electrode, the second right-hand side, this one, then the only thing that you need to do is drop the polymeric solution on top of that. Simply drop solution of the polymer electrolyte, and place the counter electrode on top of it. Just hold it for a couple of seconds so that it doesn't flow or leak out. It will automatically dry up, and the polymer itself will work as a binder. You need not to have anything else. It will dry up and become a perfect solid bind with the two electrodes. That is sufficient. And on the open table, one can do it. No need of even glove box or any sophistication. That becomes very simple and very important in the use of polymer electrolyte in DSSC. We had tested a series of polymers, different types, the synthetic polymers, biopolymers, different salts, different dopants, and achieved some of the results. I will pass through because all these I have mentioned, that doping, blending, and filler that can be added. So if it is blended, one can see that yes, works. It works. When it is added with ionic liquid, the efficiency that jumps by multiple orders from 0.017 to 0.63%. It is a big jump. Then if we add a silicon-based polymer in the carbon-based polymer, the efficiency could be even more than 1%. Different polymers, different salts, different combinations, we could achieve something close to 3% with these combinations. How to make choice of salt? Already I had shown one slide indicating the size of the spherulites, the amorphicity of the matrix. So accordingly, one can choose that if the cation is smaller, the conductivity, though it is lesser, but the property, the current efficiency, current value, and accordingly the efficiency that becomes very high. This is very similar to that which is observed with the liquid electrolytes also. And therefore, if the polymer electrolyte is used in DSSC, it behaves very similar to that of the liquid electrolytes. Smaller cation, higher current, higher efficiency. The amorphicity may be different. Efficiency that drops down. Now, one more thing I would like to indicate here, that cadmium sulfide synthesis is quite easy. We start from our undergraduate classes how to synthesize the cadmium sulfide. So we thought that if we add cadmium sulfide in the polymer electrolyte, may help in the trapping of the light. The conductivity indicated that yes, the conductivity can increase if we add cadmium sulfide, or for that matter, powder of silicon also. But interestingly, when they were used in the solar cell, Once the light was shown onto the cell was illuminated. The silicon or cadmium sulfide particles, the semiconducting particles, they form a conducting pathway and it becomes almost ohmic. The conducting pathway that gives very high current, but not VOC. So therefore, the use of filler, especially semiconducting filler in polymer electrolyte, that may not be very encouraging in case of the solar cells. This is with the biopolymers. We tried different combinations of biopolymers also with different salt, different solvent, series of biopolymers, agarose, sagopam, arrowroot, other varieties also. And accordingly, depending upon their conductivity, depending upon their surface texture and other configuration, the efficiency can go beyond 1.4% of efficiency. Now, the important parameters, though people who might have heard me talking on DSSC, they may find that these are the common slides, but I repeat that the important parameters, how to choose which material in the electrolyte. What causes the drop in the current? Is it the conductivity? Is it the cation, the choice of the cation? Is it the mobility or chain flexibility or attachment, or there is anything else which is not known to us? I believe that the size of the cation, that does matter, because it should be something that can go easily inside and come up, and therefore the size of the cation, that should not be much larger. Bigger cation that may sit on top of these channels may create a large solvation crowd, and the band bending of the oxide semiconductor, that may get affected. Therefore, one should look for a smaller cation in the polymer electrolyte. At the same time, the size of the chain, that is also very important, because the chain size will decide the radius of gyration of the polymer, and that will decide whether the polymer can really penetrate inside the holes inside the mesoporous structure or not. If the polymer cannot penetrate inside, then maybe the half part or even more part of the electrode that will remain untouched, and the efficiency will drop down. To explore all these impedance by putting a probe inside, and what now I feel that yes, it is the band bending at the interface very important, and that second the impedance, very simply see that is in fact the important part, and that is the interface that needs to be explored and understood. If we use polymer electrolyte, stability is high. The initial said that we should go. This is one of the stability is, but that we use polymer cell, and later it is up, and while drying up, so that causes bare the value of the one should look at how to increase. Otherwise, once a cell is fabricated, it remains as such for years. Now I can say the word years. One can increase the size because it is a solution of the polymer that you need to drop on that. These are the photographs from the laboratory we created at Sharda University. We tried to fabricate solar cells of more than 10 centimeter size, and that is very easily created by hand or even by a screen. And since polymer is the form of a solution, it can be simply spread over to. So unlike to the crystalline or solid counterparts, it becomes very easy if you use polymer. Just touching the perovskites, we also try to fabricate perovskite-based solar cells using polymer electrolytes. Yes, we can, and the efficiency. But the common problem of perovskites, their stability at open atmosphere, that remains the trouble. Otherwise, if you use polymer electrolyte, the efficiency, that is, I will say that is pretty good. If we can maintain the sensitizer, the perovskite structure as such, then the efficiency will be quite high. And summing up all these things, the right hand side box, you can see that when we started using polyethylene oxide as the electrolyte in dye-sensitized solar cell, the value was 0.017%. We made a target ourselves. We said that our target is 4%. And now my friends, Professor P.K. Singh and his students, they had demonstrated that yes, one can go up to 3.7% also. This value is 3.3. Okay, 3.7 also we have achieved. So we are very close to 4%. And I think that if I get 4%, I should stop working with the dye-sensitized solar cells. So if I try to conclude by a few lines, then I will say that polymers, when suitably modified, under quotes, suitably modified, works like electrolytes. The flexibility and moldability property of the polymers, they make them very important, and their use becomes very interesting. Coming down to the solar cells, one can replace the liquid electrolytes with polymer electrolytes in DSSC. It is the segmental motion of the polymer chain that makes something very important. And yes, it is the conductivity that is important, but it is not the only one. The size of the cation, their mobility, that is more important. Polymer gel electrolytes people do talk about, but the shelf life is not that good, and therefore I have written shelf life is doubtful. And then choices are open. One can try with anything. To make these complete, I should thank my supporters. Funding from Ministry of Science and Technology, fellowship from CSIR, of Eminence, Banaras University as incentive to senior teacher that I have got. Our collaborators from South Korea, from KIIT and PMU, definitely very long time spent at Sharda University, worked there. And the students, those who have worked on electrodes, on electrolytes. I had used the results of Sandhya and Anubhavi. Then people who worked on other components of this solar cell. My senior colleague, Professor Mehra, standing here, and P.K. Singh and P.K. Shuklaji. This slide I want to show because, if you look at the Google, right, DSSC, you will find a photograph something like this. When we started preparing polymer electrolyte-based DSSC, it appeared something like this. And now we are very closer to that. So it is not that much difficult and that much odd that what we prepare when we start, we can end up to something which is very similar to what we take as standard. So now we are more than 3%, so we are pretty happy that yes, we have achieved something. This is the photograph of Amaral. We established at Sharda University. Coming back to Varanasi, again, started something. And I would like to name it again as Material Research Lab at Banaras University. Before I close, though this is not exactly on the electrolytes, but on the third generation solar cell, now people are demonstrating something which is absolutely transparent. In their hand, if you can see something, it is absolutely transparent, a solar cell. The perovskite on silicon, it has gone above the theoretical limit. And the ultimate thing is that this is the laboratory wall, the colorful wall that you can see. These are made up of solar cells, dye-sensitized solar cell. So it is a colorful wall giving you beauty and at the same time some power conversion. We need to think of in this direction also. Thank you. Thank you for listening me for more than the time.
Thank you, sir. Thank you. It never looks like we were here for 60 minutes. We are still expecting more out of you. So interesting and so encouraging for us. Now the session is open for the question. If any participant has any query, they can ask. You can raise your hand or they can unmute your mic and ask the question. Any participant?
Good afternoon, sir.
Dr. Sandhya.
या
हाँ जी संजय,
कैसे है सर?
मैं एकदम ठीक हूँ। तुम्हारा ही थीसिस का सारा उठा उठा के स्लाइड बना लिया।
सर आपको सुनना तो हमेशा ही बहुत अच्छा लगता है।
अरे
आपका लेक्चर सुन के तो लगता है कि हाँ शायद हम लोगों ने भी स्टार्ट किया है।
ओहो,
अभी बहुत कुछ सीखना है।
नहीं नहीं, ये तुम्हारा ही अधिकतर थीसिस का डाटा था जो मैंने
जी
यूज कर
सर,
लिया।
जी सर, सिखाया भी आप ही ने था सर। नहीं सर, मेरा कोई क्वेश्चन नहीं था, सिर्फ आपसे बात करनी थी।
So nice, sir. So nice.
थैंक यू सर।
So nice. Anyone else? Have any question? Any query? Nobody. So I have two questions from my side. First, you mentioned that the solvent changing the conductivity in one of the slide in biopolymer when we are dispersing with DMF or some other solvent.
Right.
How solvent can affect this conductivity?
See, if the especially in case of biopolymers, it is the amorphicity of that polymer that is decided by the solvent which has been used. So वो करता क्या है कि the coiling of the chain that is disturbed by the particular type of solvent. I'm not very sure that whether it is there is any guideline or any rule that can be made out of it, but we have observed that yes, it is the amorphicity of the polymer chain, the coiling or recoiling of the polymer chain that is disturbed by the polymer. One reason may be the rate of evaporation of solvent. I'm not very sure, because the organic solvent, when we use, the rate of evaporation is pretty fast, so that may lead to less coiling of the polymer chain. And when it is water, it takes enough time to come out, so it may allow the polymer to rearrange and make further coils. एक reason ये हो सकता है, बाकी सिर्फ एक से पता नहीं चलेगा और करना चाहिए
और करना पड़ेगा। और दूसरा सर बायोपॉलीमर, जैसे हम लोग हर बार बात करते हैं बायोपॉलीमर एक इम्पॉर्टेंट मटेरियल है, बट स्टिल बायोपॉलीमर्स हैज अ चैलेंज विद ट्रांसपेरेंसी। जैसे आपने लास्ट में शो किया, द मटेरियल्स आर शोइंग 100% ट्रांसपेरेंट। इफ वी आर गोइंग बायोपॉलीमर, can we move up to solar cell preparation or fabrication with biopolymers? The transparency तो एक इशू बायोपॉलीमर के साथ भी रहेगा।
पॉलीमर के साथ शायद ट्रांसपेरेंसी का उतना इशू नहीं आएगा जितना कि सॉल्ट के साथ, क्योंकि अगर हम आयोडाइड सॉल्ट यूज करेंगे तो वो अपना कुछ ना कुछ इफेक्ट दिखाएगा। एंड जनरली व्हेन यू ऐड एक्स्ट्रा आयोडीन फॉर मेकिंग द आयोडीन आयोडाइड रिडॉक्स कपल, तो उसमें वो जो आयोडीन का ऑरेंजिश टिंच है वो आना शुरू हो जाता है, स्टार्टिंग फ्रॉम येलो टू जितना आयोडीन का कंसंट्रेशन बढ़ेगा वो कलर आने लगता है, एंड इट डज अब्जॉर्ब, वो एब्जॉर्प्शन बैंड आना शुरू हो जाता है, वो ट्रांसपेरेंट नहीं रहेगा। तो वन शुड थिंक ऑफ समथिंग व्हिच इज डिफरेंट। जो इस गेम का जो ट्रिक है वो ये है कि यू शुड हैव अ मटेरियल दैट अब्जॉर्ब्स इन IR, a material that absorbs in ultraviolet doesn't absorb in the visible region. So the band absorption band should be at UV, at IR, and nothing in between. Then it will become transparent. And if one can create something like this, then the most important application will be the greenhouse. एक ग्रीन हाउस बना के उसके छतरी पे लगा दीजिए तो वो पावर भी जनरेट करेगा, वो स्प्रिंकलर आप उसी से चला लीजिए और वो लाइट भी देता रहेगा। लेकिन अभी तक इसका जो एफिशिएंसी इवन MIT वाले भी जो रिपोर्ट किए हैं वो बहुत गंदा है,
बहुत लो है, वेरी लो,
बहुत लो, बहुत लो।
Any participant from Malaysia and Korea, if somebody want to ask a query from your side, because we have the participants from Korea and Malaysia, so I can see Dr. Noor.
Yes.
Yeah, Prof, good afternoon.
Good afternoon.
Very interesting presentation.
So, how are you, Noor? Who got stuck?
Solar cell just now. Okay, even with polymer electrolyte is still lower, but I think they still have a future, right? But what is your opinion and what is your idea to improve the perovskite solar cell using the polymer electrolyte? Because there is very few study of using polymer electrolyte in a perovskite solar cell. So from your opinion, what can you suggest, Prof?
Correct. Because if you use polymer, then probably, that can be used as even a cover. Say if you look at the crystalline solar cells, they use EVA for covering the entire system, which is a polymer, and it is cured with radiation, it becomes transparent. Very recently, I had a discussion with Ana Nogueira in Brazil, must be knowing. So she said that they use ethylene oxide, polyethylene oxide only, no salt, as a cover. So maybe we can think of making a layer of polyethylene oxide as electrolyte, having some salt, and then another layer of polyethylene oxide without salt. And the second layer may, I'm not very sure, may stop the interaction with the atmosphere. So, or any other polymer also that can be tested. So there is a very thin layer of polymer that is a sort of cover. If that can be used, then probably it will help. Otherwise, your friend Rahul will tell you how to handle it.
Yeah. Last time he also doing perovskite in Malaysia.
Yes.
Yeah, because I also read that we need to cover the perovskite from the environment. So like what you just mentioned just now, we put some electrolyte, then we cover with the hydrophobic polymer, maybe. Because before I also read they use a PMMA to coat the perovskite so that it will not interact with the environment, the moisture.
Yes, but the trouble is that it should be a thin one, number one. Then next is it should be transparent, not absorbing and allowing the photons to pass through. And then the interaction between that and the next layer, that will also be important. So if we can match all these 3-4 parameters, then definitely it will help.
Okay, thank you very much, Prof.
So finally, thank you very much, sir. You have started with very fundamentals from polymer electrolytes and taken up to the fabrication of devices, how the solar cells can work out, how we can synthesize in a very simpler manner. And this, I think, it's very fruitful, very informative for all those candidates who are working on, or they suppose started working on that, or they are working initially on that path. We have many students who are just joined their PhD. 2 of them are from Sharda University. They asked me yesterday also that we want to hear Bhattacharya sir, and we want to get details from him. And I think this is what the very, very fundamental talk which we have from you, sir. Thank you very much.
Thank you so much.
For giving such
Thank you so much.
valuable talk.
Always a pleasure to talk with friends, and I can see many people from Hindustan College and Sharda University, starting from Abhishek, and definitely Noor is from our extended group. I always take Professor Arif as my senior and friend. So it is a pleasure. Nice meeting to all. Thank you.
Thank you, sir. Thank you once again. And thanks to all the participants for joining this session. Yeah, Sandhya ma'am.
Yes, sir. Thank you, sir.
Okay, thanks. And one more announcement that we doesn't have any talk tomorrow. On 29th, we kept is blank because of Eid. So I must wish all our participants a happy Eid. And we have next talk on 30th of June. Yeah. And the next talk will be on 30th of June. Dr. Naam Adhikari will present his talk on that day. So thank you all participants. Thank you, Bhattacharya sir, once again. So I'm leaving the session now.
Thank you. Bye.
Thank you. Bye, sir. Bye. All participants, I had taken your attendance through Zoom. Please don't worry about that. I will mark it out, and at the end of the FDP session, I will share the feedback link and also the certificate generation also. You can generate your certificate out of that. Don't bother about the attendance that part. I will take it from Zoom directly. So meanwhile, thank you to all. We'll meet on 30th of June, 11:20. Till then, thank you. Bye.
Thank you, Dr. Amit.
Okay.